Are we live? Are we rolling? Okay, we are. We are live and we are rolling. First, I want to apologize. I wasn't keeping up with my grind the last couple of days for some reason. I set up a Linux update. In the meantime, before it finished, I turned off my computer. So what happened the next time I turned it on? Seems like everything was broken and out of the sync, including my graphics card drivers, because for some reason I couldn't connect my HDMI. After some googling, debugging, and troubleshooting, I found out that the most probable culprit was the fact that I think they just went kaput. They broke. So I had to install not only NVIDIA drivers, my keyboard was also not behaving in sync. My camera, I had some internet issues, internet drivers. So after installing them finally, I can say that hopefully everything will work now. On that note, I want to start the next chapter in the book. And the next chapter is called Support Vector Machines. And apart from that, let me set everything up. Let me move this guy here. It's my new wallpaper. I told you I really like, wait. No, this is not it. Wait. Which one of these does... Is it... No. What? Just a moment, because I want to move my window, my tablet window here to the top right, but for some reason it doesn't budge. No, wait. Just a second. Am I still speaking? Yeah. I am. There's... Ah, it's Alt. It's Alt. Okay, now I have it. Now I have it. Bum. I just want to make it fit properly, and then I'm gonna move it here. And afterwards, let me get in my note-taking application. Okay. It's here, and this is here, and I think I'm officially now live. Let's talk support vector machine. Let's talk support vector machines. Okay, so support vector machines. A support vector machine is a model that tries to find the best line or surface that separates different classes of data. Best line or surface that separates data. How is this related to the concept of support vector machines? Best line or surface? Best line or surface? How can I, using a mnemonic, mnemonic, yeah, it's a buzzword people use when they want to pretend they can remember something. Actually, no, it's not a buzzword. It works. I just don't know. So support vector machines, SVM. SVM, best line or surface that separates data. Okay, maybe not now. For example, look at this. Look at this. Let's say we have two types of fruit. I'm gonna use one green color. I'm gonna use one orange color. One type of fruit okay, maybe like this. One type of fruit is an orange, even though it looks like a round carrot, but one type of fruit is an orange, and another one is an apple. Okay, we want to draw a line that separates them on a graph. So an SVM is gonna find the line that separates them, that separates these two classes, but it doesn't only separate them, it is also as far away as possible from the closest apple and the closest orange. Let's say we have a group of apples and a group of oranges here, and basically a line would be, I'm doing this completely randomly without any calculations, so it might not be the best case, but basically it's gonna find a line that maximizes the margins, and this is what makes SVMs so powerful, because they can also do a plethora of tasks like classification, the thing that we just did, whether it is an orange or an apple. Okay, so regression, which predicts a number like a house price, and then novelty detection, which is a new concept for me. Novelty detection calculates whether this data point is weird or unexpected. What else? Ah, there's also something called the linear versus non-linear classification. So if our data can be separated by a straight line, like we just did it here for the oranges and apples, if the data can be separated by a straight line or a hyperplane in higher dimensions, it's linear. Again, an example: if my oranges are representing values around x equals to 1, and my apples are representing the values around x equals 5, SVM is gonna find x equals 3, and it's gonna say everything less than 3 is an orange, everything greater than it's an apple. But let's say data sometimes can't be separated by a straight line. Let's say if we have, let me move it here, a bunch of oranges here, But then I also have some apples that are surrounding the oranges. There's no way to separate this by one straight line. No matter what those ads on YouTube tell you, there's no way to do this by a straight line. So what SVM does, it uses a kernel trick to bend the space so it becomes separable in higher dimension. Basically, again, I also don't know what it means. Hey Antonio, what's up? There's this great book called, and that's the only thing I'm doing right now, it's called Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. And all of these notebooks come with it. I think the notebooks are free because they come. You can download them freely from what's the name, from GitHub. So yeah, that's the only thing I'm doing right now. But I think I made a mistake, to be honest, because this book is too. It's a college textbook, so it's pretty. I don't know how can I call it. It's dull. It's not interesting. But there are a lot of examples here, so that's why I like it. Okay, let's go. You're welcome, man. Okay. What do I have here? Yeah, we can separate data via my pen. My pen exploded. The data can be separated by a straight line. Okay. So how do we do this? We bend the space. I think we will most probably do this because I can theoretically think how this is done. The space bending. So it's separable in a higher dimension, but I don't know practically. So we're gonna skip it for now. Okay. So classification, regression, novelty detection. I think novelty detection is something that I haven't come across earlier. But it basically just asks, is this data point weird or unexpected? Is it something new? Is it something, for example, let's say we have, I don't know, a heartbeat, which goes like this. I hope it goes like this. And let's say we come across something like this. This is weird or unexpected, and novelty detection algorithm should pick this up. What else? Yeah, SVMs are really good with small datasets and small to medium datasets because they are computationally, they are slow when you have millions of rows because they have to compute distances between all points, which grows fast. But they are good for small to medium datasets because they are very powerful and precise when trained properly. They don't require a lot of data to perform well. They find the optimal boundary and they avoid overfitting better than many models on small data. What else is there? We're gonna show some visuals as well, but yeah, let's maybe just. Oh, let's mention another thing before I continue. It's the concept of decision boundary. I'm just gonna run this. We're gonna come back to this later. Look at this graph on the right, this plot on the right. A decision boundary is the line or the curve that separates different classes in a classification problem. So it's the place where the model says on this side it's A, on this side it's B. And this is one classification where we actually see this in real life, the example. We have this line, it's the decision boundary. Everything here, and it has a lot of space because it tries to maximize the margins between it. Everything here, and even new data will be what is there? the yellow one. Iris setosa. Okay. Everything right will be iris versicolor. Okay. And on the left, we actually see that we have this green model, which is broken completely. It doesn't even divide anything. And we have these other two models, I don't know what models these are, but we have the purple one and the red one. And what happens is that even though the models divided this into sections, as you can see, some elements like this yellow point here or this blue point right here are pretty close for safety. Any new potential data point might actually go beyond the border. So they are not particularly good classifiers. They don't suffer. Okay, let's do the code. Let's do the code. Let's see what's happening here. By the way, I am just a second. Yeah, I barely look at the book. I just glance the contents of the book because I think it's more important to do practical work. That's why I like these data points, because they are extremely... Oh no, did I mess this up? Yeah, I messed this up. Let me increase it a bit. All right. I don't follow the book in detail. I follow these examples because I think the best thing you can do is run it line by line, see what you can understand, see what you can't understand. For the things you can't understand, I'm just asking Google, or even better if you have tchdy or any other LLM that can help you to analyze code. And that's it. Books are too extreme sometimes. Okay. This project requires Python 3.7. It also requires scikit-learn. Just a second, please. Okay. So what's this? These are just some configs. This creates the images SVM folder, and it defines a save figure function. What I'm doing, I'm creating a pad here. I'm creating a directory here. Save figure method takes the image path, creates the figure ID with the extension, save figure. That's it. I think that's all the logic there is. Now, classification. Let's see what's happening here. Imports, I don't care. Now, this prepares the data. We load the data set, and all of the content is found here in iris. And if I print iris, what am I gonna get? What kind of data is it there? What's the structure of this text editor? Scrollable element. Ah, okay, so I have 150 rows. I thought, why can't I scroll this? I have only 150 rows and I have 5 columns, and the columns are data, which is the ID, sepal length. I think this is a part of a flower. Sepal width, petal length, and petal width. I assume this is the classify data because we have IDs that classify our flowers as 0, 1, or 2. Same thing down there. Okay. Ooh, it's a big one. Yeah, it's target. Yeah. So if let me just take another look. Where's the target here? Yeah, 5 columns. So we have Setosa, versicolor, and Virginica. Setosa, versicolor, and Virginica. And now if I print X, and if I print Y, I can't scroll this anymore. Yeah, okay. I have only these 2 properties here. And additionally, I have my targets and they're labeled. Okay, so this loads the iris dataset. I only take these 2 features to plot them in 2D. The original dataset has 3 classes, but we are gonna... okay. So we have the target and the data, and here we have only 2... what's the name? 2 classes now. Originally we had 3, but here we are only filtering the ones that are... So, wait. If I print the TOSA or versicolor... Yeah. Okay, I get it. This is how you work. Where's my pen? So I have all of this data, and I'm saying I'm creating a TOSA or versicolor, and I have this data with the ID 2, 3, blah, 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 149, 150, and let's say this is 0, this is 0, this is 0, this is 2, this is 2. What happens now is that this line of code sets true to every 0 or 1 value. So here, I'm gonna have true and true and true, and all of the 0s and 1s will be true, but all the 2s will be false. And what's gonna left here is even a smaller amount of data points. If I say here print x, I could also have print x length, but what's the 100? Makes sense. If there are 3 times of each of 1, it makes sense that it's 100 left. Okay, here, what I learned from scikit-learn and everything else is that I just pull the algorithms that I'm gonna use, the classifiers. So what I'm doing is creating a linear SVC classifier, and this C, I have no idea what the C does. Okay, the C equals 1. 1E100 will make the SVM very strict. It will try super hard to correctly classify all training points without margin violations. Okay. And then I fit it. And what else do I have? I have some models here. Okay, so this is SVC. Everything related to SVC is here. So what do we have here? We have a comment saying bad models, which are, okay, these are manually created decision boundaries with random formulas, just to show how bad or too close classifiers might behave. Oh, all right. So we have three predictions, three random predictions that are just these lines here to show how too close classifiers can behave. All right. What SVC decision boundary? So, okay, this is the decision boundary method. Let me try to understand how this works. Okay, let's skip it for now. And left is just plotting and coloring. I don't care about any of this. I want, I think the best way to understand this is to use an example. So the goal of this function is to draw the decision boundary of a trained linear SVM and also show the margin, which is, let's say, the street, this guy right here. Let's say, okay, let's do it here. Let's say we trained a linear SVM and we got this. I got W to be 2 and 1, and I got the bias to be -4. These are the weights for X and Y, and this is the bias. Okay. Okay, here we get the first line of code here in the method is we retrieving the weights and bias. This comes, maybe in our case, we created some random data, but this would come from the model's training process. Okay, next thing is here, x0 linspace xmin xmax 200. So what we want is to plot the line across the x-axis from, let's say, a certain x min to a certain x max, and this is gonna give us 200 evenly spaced values. All right. Now this is the decision boundary line, and this formula looks like this. W0 times x0 plus W1 times x1 plus b is equal to 0. Let me just get some water, sorry. Here, we are gonna solve for x1, which is this guy here. And so x1 will be, after we tumble all of this around, minus w0 over w1 multiplied by x0 minus b divided by w1. After I pull all of this data here, I have weights. This one is 2 because I pick it from the weights. This is 1, so it's minus 2 divided by 1. This is gonna be minus 2 times x0. B is minus 4 divided by 1. It's gonna be plus 4. And that's our line. This is the decision boundary. It separates the two classes. This is the line for the decision boundaries. Next thing, here, the margin line. We need to compute the margins because this tells us how wide the margin or the street should be on both sides of the decision boundary. Since we have here that V1, I mean, I don't want to select because then my tablet is moving out of focus. But V1 is 1, the margin is 1. So then we just draw the gutter lines here, and then we just plot it. I think that's the easiest thing. And then we are gonna get a plot which will look something like this. I have x0, I have here x1 or y. This is our main line. We have some margin, and these are the gutter lines at top and the bottom. Okay. All right. Now, just to come back. So, because I want to drill myself these data, these weights, and the bias, what are they? So let's say I'm drawing a line to separate two types of data, like here, apples and oranges. In a linear SVM, the decision is based on the method that I wrote right here. This is how decision is based. So we have data points, we have weights, and we have the bias. Which means that the W here, W0 and W1, which are the weights, control the tilt and the rotation of the line. And the B, or the bias, is moving the line up or down, or left or right. Now that's something that I'm interested in, how it works. Wait. Why and how? And this is mathematical. Do the weights tell us okay. So if this is our 2D space, our line or decision boundary all right. There's a lot of math here. For example, I want to understand why the support vectors lie where they lie and the distance between these two boundary lines. What? Okay, let's try to understand this. So what's the general form of this? It's f is the function of x, and I have the weights here. Plus weights 1, x1 plus b. Or I can write it in the vector form. It's going to be w times x plus b. So I have here, I have the input features, I have the weights, and I have the bias right here. And just a moment. And so if I change so wait, let me just write a simple function here. Let's say I have f of x is 2x0 plus 0.1 x1 plus the bias. What happens here? If I change x0 by 1 unit, it affects the function of x by 2 units because it's here multiplied by 2. If I change x1 by 1 unit, it affects the function f of x by 0.1 units, only by 0.1 units. And the weights that we have in our function, they tell us how strongly that feature affects the output. And a larger weight means more slope or tilt in that direction. So what's this? This is 1 and 2, and this is here somewhere 0.1. So if I plot it here, it's gonna point right with a tiny upward tilt. So the model is more sensitive to changes in what petal length. This is the petal length. Wait, what is the code saying here? Petal length, yeah, it's the first data point. So the model is more sensitive to petal length and barely responds to petal width. And that's why the weights tell us feature importance. Weights tell us feature importance. And this is basically the concept of derivatives, because I can have xe here. This means if I nudge xi by 1, the output will change by w1. It's what's the right word? It's sensitive, and let's say the big w, which means a small change in xi is a big impact, and a small w, it's barely any impact. But wait. So what's the decision boundary? What's the decision boundary here? Oh, I'm rusty with the math. I'm rusty with the math. I'm rusty with the math. I'm not happy about it. But okay, I think I understand the code here. And what is this one doing? Ah, all right. I think so. We have scales, and in the left plot we have the vertical scale, which is in the left plot. The vertical scale is much larger than the horizontal scale, but neither of these are. All of these are horizontal. Maybe this one is a bit diagonal. Okay. So what do we have here? Soft margin classification. So what does this mean? Wait. Soft margin classification. Okay. So what's this? What's this? And what's the difference between soft and hard margin classification? Soft versus hard margin classification. So a hard margin classification is trying to find the widest possible margin that perfectly separates the training data. No mistakes allowed, which means that every training point must be on the correct side and it shouldn't touch the margin, or as we now understood, we can call it also the street. Now, why can this be problematic? Two reasons. It only works if the data is perfectly separable. And let me just show it here. So it only works if the data is perfectly separable. If the data can be split with a straight line, even if you have one point on the wrong side, then there's no hard margin solution and the algorithm fails. Also, the hard margin classification is very sensitive to outliers. Even one weird point, weird points are called outliers, can mess up the model. And it will make the model generalize worse on new data. Because here on the left, we can see that one outlier, only one yellow guy here among the blue fellas, only one outlier. It's ruining the possibility of even separating the classes. On the right plot still separates them, but the boundary shifts too far just to avoid that one outlier here. Okay, just a second. So what is the soft margin classification? Maybe I should just go over the code here. So the author created some outliers, some random outliers of its own. I thought, how is it possible to have a yellow dot here when they are all grouped pretty tightly? The reason is he messed us up. Now, soft margin classification. It's okay if a few points are inside the margin or even on the wrong side. Just don't let them mess up the entire model, which gives us a balance between making the margin wide, so we generalize better, and not being too harsh about every single point. It's down here, I think. No, it's not. Is it? I think it is. Let me just skip to see if it's here. Yeah, it's here. We have C's. I'm gonna talk about this later. I just want to walk over the soft margin classification again. Oops. Hey C Shu, what's up? What's up? Okay, let me just explain this snippet. Let me just understand this snippet. I'm not explaining it because I'm also not understanding it properly. Let me understand this snippet and then I'm gonna take a quick break. We are gonna watch some YouTube videos on tech. What language is this? This is Python. Yeah, it's Python. Come on, brother. Come on. Soft margin classification. Oh, I fucked up. I fucked up pretty good. Just a second. Speedtest.net. I think my internet speed is pretty slow. Ah, maybe it's not. Seems good enough. It's 60 megabits per second good? What do you think, guys? I usually on a LAN cable, I have around 100. This is Python. I didn't recognize you because customer. Yeah, I love this. I don't know if you notice it, but my VS Code and the colors I like it's highly it just a second, let me see my internet speed. My internet speed, oh fuck. Okay, it's doable. I forgot my LAN cable. Yeah, the colors are inspired by Cyberpunk and all of the other things. I also had on certain keywords I had this glow, but I turned it off because I didn't like it. But I love these purples, these neon colors, yellows and greens and bullshit like this. Okay. So this code snippet is on hard margin classification, meaning it's trying to show us that if we have outliers, it's pretty hard or almost impossible to create a line that's gonna divide these guys right here. Or if it divides them, we are gonna have this boundary that is pretty small, and we are gonna have these big bunches of data here that are far away from the line. So let's see how this works. Okay, so on the left plot, the SVM is failing completely when we add an outlier that breaks linear separability, which means that there's no line that can cleanly one line separate the classes anymore. On the right, as I said, the SVM succeeds. We have a separation between data, but because we have these outliers here, they bend the decision boundary too much, meaning that because of them, we have to have this data right here. The decision boundary right here. That's the only place we can have it because of the way we set up the data. All right, now let's do a step-by-step breakdown. What's this? Okay, these are the two fake data points. These are the two fake data points, and both of these data points. Hey, yeah, of course. Just a second. Okay, so two fake data points right here, and both of them are added to the yellow class. What is this doing now? X01 is all right. So X01 is the original data set where we had only yellows and blues. Plus, I added, which one have I added here? The first outlier, because I limited it to 1. I do the same thing for Y. I have my labels, and I'm adding 0 to the list of my labels as well. The second one, again, I have my original data set X, and I'm adding 0, 1. I'm adding everything from here till the end. I'm adding this 3.2 0.8. Is it 3.2 0.8? Yeah, and this one is a bit bigger. Yeah. Okay. So X01, Y01 will be used on the left plot. X02, Y02 will be used on the right plot. Okay, I'm creating an SVC model here, a linear one. I'm setting the C. What is even C doing? C, what's the C doing? It's a regularization parameter. The strength of the regularization is inversely proportional to C. Must be strictly positive. The penalty is squared L2 penalty. I think as you increase C, it tries to it sets a hard margin because we have a pretty huge C here. Because it's pretty huge, it tries to perfectly separate the data, basically setting the hard margins. It's trained on the second data set. Ah, cool. There are 6 people. By the way, guys, I'm basically streaming this to simplify this to myself. If you see any value, I mean, if you understand it, please let me know if it's simple enough. Because in my opinion, in order to learn shit, you need to simplify it like as much as you can. What? Oh, half, half of the people just went. Okay. Okay. I have a huge C. A huge C, which means it's hard. It's a hard margin here. Ah, sorry. So it's a hard margin. Uh, and this guy is trained. Why is this guy trained on the second outlier? 3.20.8, 3.20. Ah, okay. So this is the second outlier. And then what am I doing? I'm creating the 2 subplots. All right, this just creates 2 subplots. I have 2 of them. Figure size, no idea what it does. They share the y-axis. Okay, now let's plot the first guy where no solution is possible. This is the first axis. So what am I pulling here? Blue square, yellow circle. Blue square, yellow circle, yes. But how? Okay, this just says impossible. Petal length, petal width, outlier. Okay, so it annotates this guy, but how does it draw it? How's this working? How's this working? Because I understand it's Python, but for some reason my brain just freezes when I see the way these syntheses are requested. Okay, let me try. Just a second. Bum. Let me pull the orange one and let's go to the tablet. So I have X01. Wait. X01. And I'm doing this. And I'm doing Y01 equal to 1. So what is this doing? So this, yeah, I know it's something like rows and columns. It's just confusing as fuck. Thanks for letting me know. I know that it's something like this. It's wait. Why is this? Give me the values in column 0 of x01. So all of the values in column 0. These are the rows and these are the columns. Give me all the values in column 0 of x01. Column 0 of x01. Ah, all right. So it's gonna give me, if it's column 0, it's gonna give me petal lengths, right? Let me test this. So print x01. I have both of these guys. But then if I do this, I should have only 0.2s. I mean, I should only have these column here, right? Am I stupid? It should be 0.2, 0.2, 0.2. No, it's getting the first one. Ah! Yeah, it's getting the first column. I'm an idiot. And this will get the second column. Okay. So this gets the first one, this gets the second one. What is this one doing? Ah, okay, this gets us a Boolean mask. Basically what we'll have here is, right, print x01 0. So I'm gonna get 1.4, yeah? 1.4 is the first value. And then if I have here print, sorry, I'm keeping a pen in my mouth. Print y01, y01. I'm gonna have 0. Yeah. Okay. So here I'm gonna pull only the values where y01 is 1. Or I'm gonna get a mask. Yeah, okay, I'm only putting the, okay, so I'm only putting out the yellow ones, I assume. And I do the same thing here. Yeah, no, it's the blue. Ah, it's the blue one, apologies. So I'm only pulling the blue ones. Why am I, for some reason I doubled it. I'm only pulling out the blue ones. Okay. Okay, let me just revert all of this. Okay, why is... I messed this up somehow. I don't know why. I don't know how. But if I run it now... Okay, now it works. Okay, let me do a quick break. Let me do a quick break. I'm gonna watch a video on something. And it's called Why Some Projects Use Multiple Programming Languages. I'm just gonna relax. I don't think I'm gonna focus. I'm gonna half watch it.
This video was sponsored by Let's Get Rusty. Today we're going to cover some low-level concepts that you probably never have to think about, unless you're working at the systems level. One of the most frequent video suggestions I receive is to explain why some projects seem to involve multiple programming languages in their development. Explaining this can be either extremely easy or extremely difficult, depending on the type of project. Take a full-stack framework like Django, for example. Python is used to handle the backend, which runs on the server, and HTML, CSS, and JavaScript to build the user interface displayed on the client side. This is a multi-language project. But in this case, It's easy to understand how everything works in production, because we're essentially developing two separate processes that communicate remotely at runtime using some form of inter-process communication. But there are other types of projects where components written in different programming languages are meant to run together as a single process. So how are these kinds of projects even possible?
What?
Hi friends, my name is George, and this is Core Dumped. If you follow this channel, I'm pretty sure you love low-level systems, and that's exactly why I'm excited to say that this video is sponsored by Let's Get Rusty. Let's be honest, Rust is no longer the language of the future, it's the language of the present. Don't take my word for it, just look at the industry. Big companies are betting big on Rust for building critical systems. Google, Microsoft, even the Linux kernel itself are now integrating Rust into their core systems.
This AI generated. I mean, this narration, this ad for Rust, it's AI generated.
That's not hype, it's happening.
I can understand it.
And if you're thinking about leveling up your Rust skills, whether for personal growth or to land a job working on real systems, Let's Get Rusty is the go-to place for Rust training. Created by a fellow YouTuber and one of the most beloved names in the Rust online community, Let's Get Rusty has helped thousands of developers, myself included by the way, master the language and break into systems programming. They're running a new cohort very soon, and since spots are limited, now's a great time to check it out. Visit letsgetrusty.com/startwithgeorge, or just click the link in the pinned comment below. Big thanks to Let's Get Rusty for supporting the channel, and now, let's get into today's video. For simplicity, let's start by considering only programming languages that compile down to machine code. Generally, each programming language has its own dedicated compiler.
Wait, this is getting too fast for me. So you have C, what's this, Rust, you have Go, you have a dedicated compiler, and all of them are compiled into
You can't just take, say, a Rust file and compile it using the Go compiler. That's where things start to get interesting, and a bit confusing. If most programming languages have separate compilers, runtimes, and memory models, how can they possibly live inside the same binary? What often confuses people is the common oversimplification that compilers are just tools that turn source code directly into executable files. Now don't get me wrong, compilers do produce executable files, but that's only the final result of a much more complex, multi-step process that we usually don't see. To illustrate this, let's look at a simple C program. If you are not a C developer, don't worry. This program simply prints a message, but the message it prints changes depending on the operating system you're running it on.
What are some directives here?
On most GNU Linux systems, the go-to compiler for C is GCC. It used to stand for GNU C compiler, but that's no longer true, and in a moment, you'll understand why. To compile and run our C program, we usually just call GCC and pass it the file, or files, we want to compile. Then, an executable is generated. From our perspective, it's just two simple steps, one to compile the program and another one to run it. But under the hood, the compiler is doing a whole lot more. Internally, GCC goes through 4 main phases to turn a C file into a working executable. Now, GCC deserves its own deep dive, but I'll break it down quickly here. The first step is pre-processing. This prepares the source code by doing things like removing comments, expanding macros, resolving conditional compilation, and crucially, resolving includes. When you use include, the C preprocessor replaces that line with the contents of the header file and all the headers it includes, effectively inserting that code into our file before compilation begins.
Man, the animations are amazing. This is a fantastic way of
So the
explaining data.
Output is still C code, but preprocessed for the next step. Next comes compilation, but not directly into machine code. Instead, the preprocessed code is translated into assembly language, which is the instructions that the computer will execute, but still in a human-readable language. So here's our first myth busted. A compiler doesn't always convert source code into machine code. In fact, many compilers convert source code into an intermediate representation, like assembly, or even into another programming language. The third step involves the assembler, which is technically another compiler, but it takes the human-readable assembly code from the previous phase and translates it into machine code, the ones and zeros your CPU understands. The result is called an object file. But here's the catch. This object file isn't runnable yet. GCC still needs to resolve the position within the binary where functions will be placed. In our simple example, we're just printing text to the console. But remember, the actual implementation of the printf function lives in the C standard library, so that library also needs to go through the same compilation steps we just described. This brings us to the final step, linking. At this stage, we may have multiple object files, some from our code, others from external libraries we included during development. The linker's job is to combine all these object files into a single self-contained executable. There are 2 ways to do this. The easiest is to take the machine code of each required function from the library and copy it into the final executable. This is called static linking. All the library functions our program needs are embedded directly into the output file. Everything is self-contained and hence ready to run whenever we want. But another option is dynamic linking. Think about how many programs on your system use the print function from the standard library. If every one of those programs statically included its own copy of that function, you'd end up with thousands of identical copies stored across your disk. With dynamic linking, libraries are precompiled into a special type of file called a dynamic shared library. On Unix-like systems, these libraries have the .so file extension, while on Windows, they are identified by the .dll extension. These dynamic shared libraries are similar to
So that's what DLL is. I kept seeing it in my game files while I was using Windows back in the day.
executable files in that they contain executable code for the functions provided by the library. The key difference is that they don't contain an entry point to start execution, which makes sense, as libraries typically don't have a main function, which is used to start a program. When our program is compiled with dynamic linking, the linker won't copy the functions from the library directly into the executable. Instead, it will simply insert a reference to the library that contains the machine instructions for that function. At runtime, if the program needs a function from that dynamic library, the operating system will load the required function into the program's address space, so the program can use it as if it were part of the executable.
What?
While this may sound a bit strange at first, it's actually incredibly efficient. Instead of storing multiple copies of the same function across different programs, the system only stores the library once. Each program that needs it simply references the shared library and loads it only when necessary, on demand at runtime. This saves both disk space and memory, a huge advantage, especially on systems with lots of programs that depend on common libraries. It's also more flexible, since you can update or patch a library without having to recompile every program that uses it. Linking, both static and dynamic, is a deep topic that honestly deserves its own video.
Yeah, this linking is like
If you're interested in learning more, let me
low level knowledge.
know in the comments, and I'll dedicate a full episode to explaining how linking works, including the ins and outs of dynamic libraries. Now back to the compilation steps.
Okay. Let's continue. Okay. So this is explained by so let's continue this. This snippet here, we load the iris file again, we get the length, we get the width, we pull data from the values, but in this case we only want print y. What am I getting here? Okay, I'm setting true or false based on whether the iris target is equal to 2. Everything else is false. Only this iris virginica. Iris is actually a pretty great name. So only iris virginica will be true. Then I create a pipeline. I create a scaler, and I create a linear SVC. Do I even have a linear SVC? Ah, yeah, this is a linear SVC. What have I used above? A regular SVC. What's the difference between these two guys? Apart from the obvious that it's most probably a lie. SVC. Okay, so I created a pipeline here and I fit my data on the pipeline. What's the difference between linear SVC and SVC? Okay, linear SVC, I assume it's linear only. It's one-dimensional because it's only a linear line, I assume. So the linear SVC is linear only. It uses a certain linear solver method, which is fast, which is optimized for large data sets. It's one-dimensional, and it's good for large, high-dimensional linear problems. But what's the difference between... I used above the SVC that uses the linear kernel. What's the difference between... I don't know. Okay, I built this assembly line, this pipeline here. I standardize the input feature, so each one has a certain mean of 0 and a standard deviation of 1. Because it's SVM. This is no, this is SVC. Where is SVM? SVM classification. Oops. Okay. It performs better when all the data is on the same scale. Okay, so we first scale the data using the standard scaler, and then we train the data using linear SVC. So when we do this, we scale X, we train the SVM model, and we keep the scaling in memory, so it will scale new inputs as well. What else do I have? A new dual equal true. It's a parameter. Okay. So I just create a pipeline here. I create some new data. I predict them. I have the decision function here. And what's there? Wait. So we just added some new data, and the first one is predicted. The first one is predicted as Iris Virginica, and the second one is not. And SVM used these scores to make this prediction, which means these measure the sign distance between each instance and the decision boundary. Okay. Okay. So I'm just gonna go get some water, and I want to finish this video, and then I'm gonna do Unity. Just a second.
You might be wondering, what's the point of all this modularization? Why break the process into so many phases if the compiler could just go directly from source to executable? Well, the reason we don't normally see all these intermediate steps is because compilers like GCC are configured by default to hide them. They just show you the final result, the executable. But with the right flags, we can expose all those phases. For example, using GCC, if you compile a program and add the savetemps flag, you'll get not just the final executable, but also all the intermediate files. We can even stop the process at a specific stage. For example, the S flag makes the process stop after generating assembly. This is incredibly useful in educational settings, where you might want to see how high-level C code translates to assembly or machine code. In professional environments, this is also used to inspect performance-critical code. You can look at the generated assembly to verify whether the compiler is producing efficient instructions. Even more interesting, we can start from any phase in the pipeline. We can pass GCC the assembly file and simply tell it to assemble and link it. This is huge, because it means we can write part of our code in assembly, pass it to the compiler at different stages, and then the linker will take care of mixing them together into an executable file. This already starts to answer our original question. Let's walk through an example. Suppose we need to write a program that calculates how many prime numbers exist between 0 and a given number, and we want it to be as fast as possible. We could write the whole thing in C.
Most probably some languages are optimized for certain tasks, and at certain point in the compilation, the data, the compiled code is injected into the assembled code. I assume this will be the
But let's say we don't trust the compiler
end goal.
optimizations, so we decide to write the heavy calculation function directly in assembly and just call it from C.
And just call it from C. But how do you call it from C? Extern int is prime. And where do I use it? Here.
Then we pass both files to GCC, which will compile and assemble the C code, assemble the assembly code, and link both object files into a single executable file.
Cool.
And voila, we've just compiled a multi-language project. This technique is used by real-world systems like the Linux kernel, FFmpeg, OpenSSL, and many embedded projects. They often contain C for most of the logic, but fall back to assembly when performance really matters. Now, here's a fact that a lot of you might have already concluded, but I'm still going to mention anyways. What we casually call the C compiler, like GCC, isn't just one compiler. It's actually a toolchain, a pipeline of tools that are executed in sequence. Each stage consumes the output of the previous one, and each of these tools is pluggable. We can replace parts of the toolchain or feed in our own files at various points. This is why GCC doesn't just support C. It also supports C++, Objective-C, Fortran, Ada, D, and even Go, depending on how it's configured. Originally, GCC stood for GNU C compiler, but over time it evolved into a compiler suite that supports many programming languages beyond C. Because of this expansion, the name GNU C compiler became misleading, so the acronym GCC was redefined to mean GNU Compiler Collection. I think this is really important to understand. Every time someone casually calls it the GNU C compiler, it can unintentionally reinforce the idea that this whole system is a single black box that transforms C code into a runnable file. But the truth is, it hasn't been just that for many years now. Okay, but assembly isn't for everyone. And to be fair, since assembly is already part of the compilation pipeline, using it feels a bit like cheating. So what about mixing high-level languages instead? For example, instead of writing a function in assembly, what if we implement part of our project in Fortran? Well, this is totally possible, and actually more common than it might seem. In this case, however, we usually need multiple steps. One to compile and assemble the Fortran file, another one to compile and assemble the C file, and a third to assemble both object files into a single executable. Unlike assembly, which is already embedded in the C compilation pipeline, Fortran has its own pipeline, its own compiler, and sometimes even its own runtime dependencies. And by now, it should be super clear that the answer to our original question, how can different languages live inside a single executable, comes down to the linker. You see, the different languages involved don't even need to come from the same compiler suite as GCC. Take Rust, for example. It has a completely different toolchain from C, different compiler, different build system, and a different philosophy altogether. I could spend hours talking about the insane engineering behind its compiler. But what we care is that when it comes time to produce the final binary, guess what? Rust, too, relies on a linker. So if we want to call a Rust function from C, here's how we do it. We implement the function in Rust. We compile the Rust code into a static or dynamic library. We declare and use the function in the C code. Then, we compile the C code and link it with the Rust compiled library.
Cool.
And of course, it works the other way too. We can call C functions from Rust. It all depends on what we're trying to achieve. In fact, it's more common to call C code from Rust than the other way around. C is older, and many mature libraries and system APIs are written in C. Rust developers often need to hook into that existing ecosystem, especially in areas like graphics, cryptography, or operating system APIs. There are several reasons why you might want to mix multiple programming languages in a single project, but another one that comes to mind is performance. In many projects, the entire system doesn't need to be blazing fast, just certain parts. So what a lot of developers do is write most of the project in a high-level language for convenience and development speed, and then implement only the performance-critical components in a lower-level language like C. Before we wrap up, there's one more really important point to understand. Let's say we have two high-level languages, language A and language B. Just because both of them have a final linking phase doesn't automatically mean they can be correctly linked together into one executable. Here's a very simple example. We've implemented a function in language B, and we're calling it from language A. Even if both compilers emit assembly for the same architecture, they might make different assumptions about how data is passed between functions. For example, the compiler for language A might pass the two function parameters in registers 0 and 1, but the compiler for language B might expect the parameters in registers 1 and 2. Both are producing valid machine code, but since their calling conventions differ, the result will be undefined behavior at runtime. Language A will place arguments in the wrong place, and language B will perform operations using incorrect data. And it doesn't stop there. In this example, there's another problem. After computing...
Okay, let's continue. I did a bit of a magic here. While we were watching the video, I turned off machine learning and I pinged and I opened Unity, and the last time I stopped, I did the most basic things. I just created two game objects and I'm playing with them. So if I click, okay. We have all these components. This is the cube. Is this the cube? It's named the cube, but it's a sphere. We can change it. I changed the mesh to be a sphere. And then I need a collider. Circle collider? Yeah. Can't add component circle collider. Why? Why? Okay, video cards nowadays can handle highly detailed model. It can render it. The physics system is executed in the CPU, and it needs to do complex calculations in order to detect collisions. We need to run our game at least in 30 frames per second for the game to be decent, to have a decent performance or a smooth experience. So we need to change. We have the mesh filter and the different types of colliders separated. One handles the visual shape and the other handles the physical shape. Okay. So what do I have here? Just a second. Okay. That's why I have the mesh filter. That's why I have collider components separated, because one handles the visual shape and the other the physics shape. All right. Because that was my question basically. Why is the collider and the mesh filter separated? Just a second. What else do we have here? All right, so I need to create a new collider because I had the box collider here somewhere. I did, or the rigid body. Can I remove the rigid body? Remove component. What if I play it now? Ah, I need a rigid body in order for this to move. Rigid body. Collision detection. How can I... Okay, I fixed the issue of my sphere appearing as a box. Okay. I also removed the box collider. And then if I go add component, where's the physics here? Physics. Joint sphere collider. Sphere collider. I need to add the sphere collider, right? Yeah. Now, if I click play, what will happen? It's loading, just a second. If I click play, why? Oh, it didn't do a good job here. Is it because of my radius? Where's my camera? What's my camera looking at? Can I move it? Can I move it down? And can I rotate it somehow? How do I do this? I forgot all of this. Rotate. How? How can I what? Can I see some? Okay, just a second, just a second, just a second. Just a second. No, I don't want this. Yeah, I want this. But I also want this. Will this work now? Will it? I'm doing something wrong, definitely. Oh God. God, can I reset it somehow? Okay, rotation 0, 0, 0. Now, if I play again, okay, okay. I think I'm fine with this. So why Unity? Let me go back to my circle, to my sphere. What's the difference between the mesh filter and the collider? The mesh filter is what we see. The mesh filter tells Unity what 3D shape to draw on the screen, like a cube, like a sphere, like a character. It's purely visual. So we have here, it's purely visual. We have no physics, no collisions, no gravity. It's the skin, it's the appearance of our object. And then we have the collider, it's what you bump into. The collider tells Unity how the object should physically behave in the world. It defines a shape that's used for collisions or triggers or physical calculations. It doesn't care what the object looks like, it handles math for physical interaction. Again, why keep these guys separate? Because we have performance. We have physics is being handled by the CPU and the rendering is being handled by the GPU. If Unity tried to use the complex shape from the mesh filter for physics, the game would slow down. It uses simple collider shapes like boxes, spheres, or capsules that are, let's say, much faster to calculate on average. Okay, Okay. Okay. Wait, what's this? What if I select this? Ah, wait. This is a sphere. I don't want a sphere here. I want, let me remove this guy. I want, what's the name? Box collider. And now if I click play, will it work finally? It should. It should. Nice. My first collision. My first collision. Okay. Some complex objects will need to be separated into sub-objects, and each sub-object will have its own components. And these sub-objects, okay, as well need to be part of the main object. So they are all working and living in unison. I think most probably this is used for, where's my tablet? Here. I don't know. Let's say we have a 3D human, and what I assume is that the head is a separate object. I don't know. The arms are separate object, sub-object. The legs are a separate sub-object as well. Okay. So we can create an object that is a parent of another object, and they will be related to each other. Okay. And there's something called wait, a transform relationship. Transform relationship. In this relationship, a child object will be part of the parent's transform. It will most probably increase its size when the parent increases its size, and it will follow it as if it was attached to it. Like, I don't know, maybe your model is holding something in their hands, like a sword, which means that the sword will follow the hand and the model while it is attached, basically. Okay, let me just make a quick, let me finish this video because I'm really interested in what.
Computing the result, the function writes it to register 1 and returns, but language A expects the result to be in register 0. So not only does language B compute the wrong result, but language A doesn't even see or use that result at all. The same example, but this time with two languages, X and Y. Here, both languages use register 0 and register 1 to pass and receive parameters. But let's say language X uses pass by reference for all function arguments. It puts the addresses of variables in the registers, which is not the same thing as putting the values of those variables directly in the registers.
What loads the value A into register 0, loads the value B into register 1?
Meanwhile, language Y passes by value, so it expects the actual values in the registers. That's why here, it immediately add the content on those registers as soon as being called. At runtime, this mismatch causes language Y to interpret memory addresses as actual values, adding those addresses instead of the values stored at those addresses, leading to completely wrong behavior, or even a crash. So even though both compilers produce valid and executable assembly, the final linked binary is inconsistent unless both sides agree on how to talk to each other. These kinds of low-level rules are defined by what's known as the Application Binary Interface, or ABI. Just as an API defines functions at the application level, an ABI defines how different components of binary code interact with each other through the hardware. So, when we're mixing two different languages, it's not enough that they both produce object files. At least one of them, or specifically, the part of it that interacts with the other language, must conform to the other's ABI expectations. In our language X and language Y example, one way to make this work is by modifying language Y to dereference the values. That way, the function will first fetch the data from the memory addresses provided, loading the actual values into the registers before performing the addition. In this case, language Y is being made to conform to the ABI expectations of language X. But we could also take the opposite approach, make language X conform to the ABI expectations of language Y, by simply loading the argument values directly into the registers instead of their addresses. This way, the function this function will interact with code.
Okay. Let's continue. So, transform. Let's create this. This is gonna be a good example. So what I need to do is I need to create an element that is gonna represent an enemy, and another element is gonna represent the weapon of the enemy. So I'm gonna go 3D, cube, sphere, capsule maybe? Okay, capsule is good. Where are you, brother? How do I focus? There's a... it's focus itself. Alright, so I have the capsule. Okay, I have all of these things here. How can I transform it? Like this. Okay, so this is the capsule. And then I'm gonna create another 3D object. It's gonna be the cube. But the cube needs to be smaller. Maybe not like this, but like this. And it needs to be like this. Alright, let's say this is a bazooka and this is our enemy. And they are carrying a bazooka. So this is how I created this game object combination, but now I want to keep the wait, let me select this. I want why can't I select this guy? Okay, if I move this object, the weapon, which is the other cube, will keep its position. It won't follow this model here. So what I need to do is I need to drag the weapon to the enemy in the hierarchy window. So I'm gonna say this is, can I change the name? I should be able to change the name, rename weapon, and this will be enemy model. And if I pull the weapon here and put it to the enemy model, now if I move the enemy model, we also have the weapon, this improvised weapon, moving together with it. So if I move this capsule, I'm gonna see this other element, this cube, also moving, also rotating and being scaled with this. So if I, what's this? So if I rotate this, how do I rotate? Yeah. Cool. So why would I use transform relationships? Because Okay, we can organize our elements here better. We need a good way of keeping track of our projects, blah blah blah, all of these things. Okay. Okay, so I could basically do the following as well. I can copy this, and I have copied this model, and now if I move it, no, I didn't want to do this. I wanted to move it out of, no, wait, like this, yeah. Now I have two of these guys. I could create a new folder, an empty game object, and I could drag all of these in this empty game object, but I don't want to do this. Okay, what else can we do? What else can we do? My dream is to make a game, and this is just the basics, but I think I'm gonna do this. Okay, I need to change the pivot of an object. If I try to rotate my gun now, wait, can I move it? I can move it. So if I try to rotate, it will rotate around the center. Yeah, because I put it here. But I need to rotate this around the way where my characters are looking at. Wait, let me select this again. But I can move it, right? Interesting. Now, what do I have? I have two of these enemies, and I have this thing right here. Not interesting. Okay. Wait, let me just see something on YouTube. 2D games made in Unity. Next level 2D games made with Unity, alright. Alright, I want to make something like this, like an isometric game. maybe even more isometric than this. Cool. Cool. A lot of good games were made in Unity. So what's the next thing? All right. So what are prefabs in Unity? So what's a prefab? A prefab is like a template or a blueprint of a game object. Once we create a prefab, we can reuse it multiple times in our scene or code. We can update the original prefab and all its instances update automatically. And we can use it to spawn objects like enemies, bullets, or power-ups during gameplay. It's like, let's say we made a robot with a bunch of parts. Rather than rebuilding that robot every time, we turn it into a prefab and then we can drag it whenever we need one. And how can we create one? Let's see. So I can drag my custom object from the hierarchy window to the project window, and there will be a new asset. So if I do this, if I put it here, I have it. I have this enemy here. Okay, so there's a problem, and I can do it. Yeah, I can just put it here, and it's blue. This is great. This is really good. I didn't know about this. How can I move this enemy now? Like here. But why is this not blue? Why is this guy not blue? I know that blue most probably means this object is an instance of a prefab. So if I click on this and if I go to, wait, where's my inspector here? Inspector, and yeah, here's my prefab enemy model. Cool. Oh, I need to go. It's already 2 hours. I'm really sorry. I'm gonna continue this some other time. Let me just save this and see you